Good afternoon, everyone. I am Pratusha Das, a PhD student at University of Southern California. Today at ICIP, my presentation topic is Application-agnostic spatio-temporal hand graph representations for stable activity understanding. This work has been done in collaboration with Mitsubishi Electric Research Laboratories. So in this talk, I'll first cover some preliminaries on hand graph and graph Fourier transform. Then I'll move on to my proposed method and talk about two applications. And I'll also talk about the stability analysis of our proposed method with two novel stability matrices. Then I'll move on to our experimental results, and then I'll conclude my work. So the main design goal of this work is to design a stable model for hand activity analysis. For that, we have represented the hand skeleton data as a spatiotemporal hand graph, and then we propose two new stability matrices to analyze the proposed method. Hand skeleton data has many applications, for example, worker monitoring in industry, food preparation, and security and surveillance. The use of hand skeleton data has many advantages over video. For example, it preserves the privacy of the scene. It is very robust to sensor noise and efficient in computation and storage. We can represent hand skeleton data using hand graph very efficiently, and it has shown very good performance in past. In our paper, we are proposing a spatiotemporal graph representation, and we will show that these representations are application agnostic and not data driven. And we will also show that this method is very stable with any external changes. So in literature, there are work on full body skeleton data where people used graph-based method, but there are very few works on hand skeleton data, and the work which is there in literature used very complicated model, for example, LSTM or temporal convolutional network with temporal transformer network, but all of them needs a lot of data. But sometimes there are cases where we do not have any information or any data available for the task. In those cases, we will be able to use this spatiotemporal hand graph representation. In our case, we will use two spatial graphs. First one is finger connected hand graph, which was proposed in our ICAS 2019 paper. And the second one is left-right hand graph, which captures the relative motion between two hands. Both of these hand graphs are fixed and undirected. So given a graph with vertex set V, edge set E, and adjacency matrix A, we can define the Laplacian matrix as a difference between the degree matrix and the adjacency matrix. And if we do a eigenvalue decomposition of this Laplacian matrix, the eigenbasis represents the graph Fourier basis, and corresponding eigenvalues gives you the graph frequencies. So in this case, lambda represents the graph frequencies, and we can easily interpret the basis, the graph Fourier basis for these hand graphs. So as you can see here, some examples of graph Fourier basis for finger connected hand graph. And for this lambda equals to 0, the graph Fourier basis is basically capturing the average of the graph signal present in all the nodes. The lambda equals to 0.42 captures the variation of the signal present in your little finger, thumb finger with respect to the rest of the fingers, and so on. This is some examples of graph Fourier basis of the left-right hand graph, and these graph Fourier bases are interpretable, and that's the beauty of using this graph-based method. And as you can see, the lambda equals to 0 captures the average of the signal. Here lambda represents the graph frequency. Lambda equals to 0.26 captures the variation of the motion between your left hand and right hand, and so on. So let's move on to our proposed spatio-temporal hand graph. So spatio-temporal hand graph, the one we have used here, is nothing but a Kronecker product between your spatial graph and a line graph. And you can represent the graph Fourier basis of this spatio-temporal hand graph as a Kronecker product between the graph Fourier basis of this spatial graph and the line graph. And if you want to capture the temporal information for a temporal window, let's say 10 seconds, then you can increase the length of this line graph to 10 and or the number of frames, and then you do this Kronecker product, and then you can capture the information of the temporal window. There are many other ways to do or make the spatio-temporal hand graph. For example, you can connect all the nodes of one frame to the other. But why we are using this kind of STG hand graph? Because these hand graph representation is separable. So you can first apply this hand graph, and then you can apply the line graph basis to extract the features. So given your graph signal xi and the graph Fourier basis uk, for this case uk is nothing but the columns of this psi j, we do a dot product between this uk and xi, and you get the final graph Fourier coefficient alpha ki, which represents your features. So for now, I'll move on to our first application, which is unsupervised action segmentation. In this case, our motivation or the goal was to do or have a qualitative analysis of participants in an industrial setting. And as I mentioned, this is unsupervised. That means we did not have any information about the task, what task they are going to perform, what are the motion patterns or anything. We just knew that this longer task has 3 smaller subtasks, and that's why the first goal of this work was to divide each participant's data into smaller segments. And to have a qualitative analysis, we had experts data. And to have this qualitative analysis, after segmenting each participant's data into smaller segments, we computed a similarity between the participants' data to the experts' data using a dynamic time warping based method. So this is the data set. 11 participants performed the complete task 3 times. So first time they did not have any information what they're going to perform. And the second time they already did the task 1 time. So in the second time we were expecting that they will do it in much more better manner, and so on. And we had 1 expert's data. So, and as I mentioned, the task had 3 smaller subtasks: assembling, combining, and checking. So first, we divide each participant's data into smaller windows, and then we extract features using our proposed method, which is graphics method. And then we use a clustering approach with cluster number 3. So here we are using expectation maximization Gaussian mixture model. After we have the cluster labels, so if there is any temporal transition from one window to another window in the cluster number, we consider that as segmentation instance. So once we have this smallest subtask of the segmentations, we compute the similarity between the participants' data to the expert data using a dynamic time warping based method. As we all know that dynamic time warping is highly sensitive by the length of the data. So we normalize it by the length of the 2 data points, A and B. I'll just show you in the next slide. So now I'll move on to the results. So here I'm representing the segmentation accuracy in this table, and the features I'm comparing against is the motion vectors. So if I use the raw motion vectors extracted from your software like OpenPose or Kinet, and use them directly as features. I'm also comparing with a spatial graph, which is used in our ICAS 2019 paper, and obviously our graphics method. And as you can see that graphics is outperforming all these other features. So this is an interesting figure. So as I mentioned, the DTW is normalized by the maximum of the two length of the two data points. And here the blue color means each participant's first performance or first iteration. Red means participant's second iteration, and yellow represents the participant's third iteration. And we expect that in the first iteration, the similarity, they will not perform the task in the best manner. So the similarity will be not good. So the DTW value will be very high. And in the second and third, it will decrease. So we'll have a decremental pattern. And most of the cases we found that pattern. Okay, now I'll move on to my second application, which is a complex action recognition task. In this task, we use our graphics method to extract the features, and then we use a SVM-based classification model to recognize the task. For this case, we are using first-person hand action dataset, which has 1175 data points. 6 different subjects are performing 45 tasks in 3 different scenarios, interacting with 26 different objects. But in our case, we are only using the skeleton information. We are not using any background information or any object information. We will be using two experimental settings. In the first setting, we are changing the train test ratio. In the second setting, which is a cross-person setting. So in this case, while training, we are using 5% dataset, and during testing, I'm using the 6% dataset, so that the model did not see any data from the 6%. So this is a more real-life scenario. So if you see the results of recognition accuracy in a 1:1 protocol, you'll see that our GraphX method is almost giving you comparable results with the other existing method. But the most interesting part here is in the cross-person setting, our proposed method is always performing good. So which is a more real life scenario, and we expect a better model for this kind of situation. Now I'll move on to the stability analysis. So we all are aware of the leave one out cross-validation stability, but here we propose 2 new stability matrices. First one is loss function stability. So in this case, we are considering the variation of the loss function value of the validation set and dividing it with the mean of the loss function value of the validation set. And the second one is estimation stability with cross-validation. So this is inspired by estimation stability in Lasso. Here we are considering the variation of the validation set class probabilities. And why it is important, consider a binary classification problem where you set your threshold as 0.5. So let's say your class probability sometimes is 0.6 or 0.9 for the same class, but always you'll get the label as 1. So we do not want such variation in the probability, but this information will not be captured by leave one out cross-validation stability, but this will be captured by this ESCV. That's why we are considering this one as a stability matrix for our case as well. So if you use these three stability metrics together, we will have a much stronger sense of stability. And if you see the results, our GraphX method is performing good in all the cases. So we have seen that it is performing good in cross-person setting, and it is also a very stable model. So to conclude my work, we have proposed a spatio-temporal hand graph representation, which is application agnostic and unsupervised. So it does not need any data to build your model. And we have shown application in two different scenarios and proposed two new stability matrices to analyze the classification model. Thank you, and please email me for any questions.